topic for discussion is diffraction. What do you understand by diffraction? So before I explain anything, just one question for all of you. If I draw a diagram, suppose we all are moving, going for a picnic, but in a hilly areas, and we are traveling. And suppose let me draw a hill. A hill is here, and our car, our school bus is here. I can't make a bus, so let me get the bus is here. This is a bus. We are carrying our mobile phones, okay, maybe other digital devices to reach the signal. Means a hill is there, and we are passing across a valley, and then signal to be reached to the bus. What kind of signal? Suppose I have a signal is coming from here. Signal is coming from here. And suppose that the signal is reaching to the point, the person who are living, some of the tribes are there, some of the people are living there. And so let me draw this kind of diagram, something happening here with the signal. Suppose if the signal is able to reach to this point, to the bus, what phenomenon is this? What phenomenon is this, children? That is my question. What is happening here?
Diffraction.
One more thing, children. Let me add, then I will give you some time, children. I'm here in this classroom. Even you are sitting in your class, in your room, children, in your sitting room, in your study room. If you start talking with me, then your parents who are just next to your in another room, they might hear your voice, they might hear your sound. Why? How it is possible that my sound, my voice is going outside this classroom? The person, the supervisor, if anyone traveling outside the corridor, she can hear my voice, my sound.
Is it Doppler effect?
Even that the Doppler effect, okay. Even the rooms are closed, windows are closed, still my voice is going, sound is going outward. That the first thing, children. Okay, first thing. Are you agree that the voice or the sound will go outside, and the person who is standing outside the room will be able to hear my voice? Even the voice clarity may be different, but still she can interpret that the someone is talking in the room.
That could be possible.
Yes, sir.
Okay, that
Yeah,
can
it
be
could be
possible. Good. Now the third situation is light. I'm here in this classroom, light is there, door is closed, the windows are closed, and maybe that the some part of the light can go outward. Light can go outward. Suppose outside this room there is a dark room, and I'm sitting in a bright room, then the some part of the light will be able to go outward. Light can be feel that light can, you can see that the some part of the light will be go outside. But again, the one thing, I can change the statement in this way. If someone is sitting outside the room, I can't see because the wall is there, a door is there, I can't see who's standing outside. But my voice can reach to that particular person. So it means that light, because I can see the person with the help of the light helps to see the objects. I can't see the person, but the person can hear my voice. So the two things are happening here, children. Let me come back to the explanation. Before I explain, now I want to listen to you, children.
It's because like when you want to see objects, light basically reflects off the object to your eyes so you can see the object, but that's not necessarily the case with sound because you could still hear a person from another side of the wall. But for light, it reflects off an object into your eyes so you could see it. That's why you cannot really, you see the wall and not the other person on the other side. Because that's the first thing that's reflected into your view.
Okay, let me draw one more diagram. Suppose this is a door. Okay, this is a door, and door means that some part of a room, and light is there. Light is there in this room. But if I open this door, outside the door, just remember that the situation is there is a darkness. Okay, there is a dark. Other side that the rooms are the corridor that are dark. No light is there. If I open the door, if I open, what happens, children? If I open it, then what happens? When I open it, then the light from this door will move like this. Means in this area, I can see from the edges of the door, I can see that some light can be seen in this area outside the door, children. At the floor, I can see the light. But here, to this entire portion, that is the darkness is there. No light is there. Even again, the same situation. I am sitting here, a person is here, and someone is speaking, and someone is standing here. Someone is there. The other person is also there, the other person. But my voice can be here by this person. Instead of that light is not going to hear, but the voice that the sound can be heard by the other person who is nearby to the door. Now, all these things, what is happening in this case, children? This is all due to diffraction. That is our topic of discussion, diffraction. Diffraction. Today we are not talking about anything about reflection or refraction because we have done in our previous lessons. Diffraction, children. I have taken one example in a hill. Light signal can be diffracted. Diffraction is basically what, children? Diffraction means spreading of a wave. Spreading. If it is a sound wave, spreading of a sound wave. If it is a loud light wave, the spreading of a light wave, that phenomena is called a diffraction. Or there is another definition, another meaning of diffraction, bending, B-E-N-D, bending of waves, whether it is a sound, it is a water wave, it is a light wave, means electromagnetic wave. Bending of waves around the corners, around the corners, or obstacles. I hope the spelling of obstacles are correct. So obstacles, bending of waves around the corners. Corners means at the edges or the obstacles. That phenomenon is called diffraction. So diffraction is basically bending or spreading. So in the previous case, then when I was talking about if I open a door, then the some part outside the door, in the some region of space, there will be a light, but the sound covered more area. It means I can say here sound diffraction, diffraction will be more in sound wave as compared with the light wave. And this phenomena, diffraction, children, this completely depends on one factor, and that factor is the wavelength that we are going to discuss. The question is that light diffract, sound diffract, water wave diffracts. But these diffractions means the spreading of a light or sound or a water waves, it completely depends upon the wavelength of the wave. Now listen carefully, children. Please pay attention. In our day-to-day life, children, we come across various objects whose size are comparable to, listen carefully, children, whose size are comparable to the sound wave, means comparable to the wavelength of the sound wave. Sound wave wavelength. What I'm saying, children. The question is why sound wave diffract more as compared to the light wave? And the simple answer is you need to find out what is the wavelength of a sound wave, what is the wavelength of a light wave. I'm talking about that the objects we come across. If you just check your door, the length of a door, 1.5 meter, 2 meters. There are small gaps are there in a door, in a windows. There are certain gaps are there. The thickness and the edges, there are small space that the openings are there, gaps are there. So this length of these obstacles, of these gaps, is comparable to the wavelength of sound wave. What is the wavelength of a sound wave basically? How much is the wavelength of a sound wave?
330 in the air.
330 meter per second, that is the speed.
Oh, okay.
Speed of a
Doesn't it
sound
depend?
wave.
Doesn't
Mhm.
it depend?
It,
It depends.
even with this topic, we haven't discussed that the audible voice, sound 20 hertz to 20,000 hertz.
Oh yeah, that's the human
That is
hearing.
the frequency. So from the frequency, you can also calculate, frequency is inverse proportional with the wavelength. So basically, a wavelength of a sound wave in centimeters. It is in centimeters, in a few centimeters, and that is equal to the wavelength, or sorry, the gap or the spacing of the objects or the obstacles we come across in our life. But if you look at the example of a visible light, from the electromagnetic spectrum, visible light, this portion still we haven't done. Electromagnetic spectrum is there in the next chapter, number 7. Visible light. Visible light has a wavelength from around 350 to 750, around. This is not a perfect answer. You can check later on the Google. 350 nanometer to 750 nanometer, around this value, something in this range. 350 is around for the violet color and 750 for the red color. There may be some variation in this range which I have written here. 350 to 750, children. That is the wavelength. Nanometer, nano, 10 to the power minus 9 meter. Means 350 times 10 to the power 9 minus 9 meter. So the question is, children, that diffraction, to see the diffraction effect maximum, that the wavelength of the incident wave, please make a note of the statement, children. Wavelength, wavelength of what? Of a incident wave, that is lambda, if it is equal to or nearly equal to the width, oblique gap, or obstacle size, then diffraction will be maximum. Diffraction will be maximum. This is the one condition. Diffraction will be maximum. For example, children, let me draw a diagram. And then I will go to the cognitive. So here I have an obstacle and there is a small space, a gap is there. And the width of this gap is suppose h centimeter or in meters. I have an incident wave. A wave is coming, maybe a water wave or a sound wave. This is a wave coming, and this is the wavelength of the wave. The crush or compressions, consecutive crush or compression will give you a wavelength. If this lambda, if this lambda, children, lambda means the wavelength of the incident wave is equal to h, then what happens? There will be diffraction. Diffraction will be max. signal. And if I draw a pattern of diffraction, so how will it look like? Let me draw the diffractions. Spreading, as the questions of diffraction is, it is spreading of wave. Wave will spread with the same wavelength as the wavelength of the incident wave. So remember, be careful, children. When you are drawing this pattern, remember this length and this length of the incident wave should be same. So this is basically, this is spreading. This sound is spreading. So this is spreading, this is spreading. Remember that again, I have drawn a large distance, but the gap should be same in every compressions or a crusts. This is a diffraction, children. On the other side, on the other side, on the other side, let me draw another diagram. If I take, this is a gap, and we have again a sound wave or the water wave like this, whose spacing is, you can see that this is lambda. So in this case, lambda is less than this gap or the height or the width of this gap. Diffraction still there, diffraction will be there, but it will be a minimum diffraction. Minimum diffraction means this sound water wave, they diffract but very less. So how would you draw a pattern when diffraction is minimum? So diffraction is minimum, something like a square bracket, something a very small curve, still the spacing should be same as the incident wavelength should be same. And diffraction, you can observe the diffraction, it is spreading, but the diffraction will be less. So that kind of a diagram you have to draw, children. Now let me go to the topic. Now, any questions till now, children?
Sir, you said the distance between the wavelengths will be the same. Oh, sorry, the difference between the compression
Wavelength should be
will
same.
the same.
In the diffracted
Yeah.
pattern, that the wavelength should be same, that your drawing should be perfect, as the incident wavefront length and the diffracted length, that the gap should be same. Even here in my
Sir, will
drawing,
there be any incident where it won't be same, like any inequality that will result it in not being same?
in diffraction this will be same, but in refraction we have seen in the last class, this gap, it change. Wavelength of the refracted ray can be higher, can be lower. It depends upon how the water wave or the sound waves they are traveling from what medium to another medium.
Oh, okay, sir. Thank you.
In
Sir, can I ask
refraction,
a question?
yes, please, Kezia.
Before you gave an example of sound and light, the example of not seeing a person across a wall, but hearing their voice, could you explain it in the terms of diffraction, please?
Yeah,
Or
diffraction, yeah, Kezia. Let me explain. So now what happens? I'm here in this room, and my voice can be heard by the person who are outside, because my voice, what's happening here, the energy, it has certain wavelength. Sound wave has a wavelength, and this wavelength is in a few centimeters. If you calculate, from 20, okay, just let us calculate a value. Let me go back to the white paper. If I take the minimum value, suppose 20 hertz, frequency is 20 hertz, minimum frequency of sound wave, I need to calculate lambda. As you know, frequency is equal to 1 by lambda, that is by lambda equal to 1 by f. 1 by 20 is how much? Please calculate
yes,
some. How much? Again, zero. This much. If frequency is in hertz, it's in hertz, so this wavelength is in meter. 0.05, and basically 0.05 meter means, can we convert into centimeter? 0.05 meter, or around how much centimeters? 5
5
centimeters.
cent.
5 centimeters.
5 centimeters, yeah.
5 centimeter, that the edges, the thickness of the walls or the gaps, that is something about in this range, 5 centimeters. All the obstacles actually they are in centimeters or in meters. That is equal to the comparable to the wavelength of the sound wave. Because in light waves, the wavelength is in nanometer 10 to the power minus 9 meter, that we cannot see even. Are you getting my point?
Oh,
So this
yeah,
is in
yes.
centimeters. We come across the object that we can see. They have a particular dimensions. We can see, we can touch them. But in case of the light wave, the wavelength is in nanometer, 10 to the power minus 9 meter. That is very, very small. These small objects are not here. We can't see that 10 to the power minus 9 meter millimeter objects. We can't see.
Like those little gaps where the diffraction happens, we can't see through it.
Yes, this diffraction phenomena, you can understand, children, with one important point. This is completely related to the wavelength of the incident wave. If the wavelength of the incident wave is equal to the obstacle's height of their width, then diffraction will be maximum. Otherwise, it will be minimum. It will spread, but with a lesser amount. Now, children, I have taken one example of in a hilly areas. In a hilly areas, if I need that the signal should reach to the person who are living in a valley, what kind of wave should I use for the transmission? That in the digital communications, a satellite signals. What kind of a wave I should use? Okay, let me draw a diagram. This hill, a house is here, house is here. The signal should reach the bottom of this house, means person who are living here. What kind of wave should I use? I need to use a wave whose wavelength is very, very large. How much? I can see that this is the top of a hill, and this is its width. If the incident signal wavelength, this is the incident signal, if the incident signal width is equal to the h, or the width of the hill, in that case the diffraction will be there. Diffraction is possible there, and due to that a signal can be reached to there. A person who is here can receive the signal if this is a wave, incident wave, whose wavelength is very, very large. So that's why we use a radio wave. Radio wave, again, children, that this is the part of the chapter number 7, electromagnetic spectrum. Radio waves, microwaves, infrared radiations, or gamma rays. These are the part of the next chapter, but still, radio waves are ADI, radio waves has higher wavelength compared with other kind of radiations in the electromagnetic spectrum. So now, children, here you don't get confused about, sir, what is this radio waves? You never teach us about the radio waves. This part we will discuss in our next chapter. But remember, here we are talking about the diffraction. Diffraction is maximum or minimum depending upon the wavelength of the incident wave.
Sir, now the like headphones or earphones we use, they have the smaller distance between the wavelengths, right? Incidents.
What kind of wave you're talking?
Sir, I'm just talking in general of like wavelengths that the sound waves that are transmitted through like earphones and all.
Sound wave, sound wave has a what kind of
I
wave?
know it has like a whole variety. I'm not able to specify it.
There is a difference between the wavelength of a sound wave with the wavelength of the light wave. There is a difference. Sound wave has higher wavelength as compared to the light wave, as compared with the visible light, that the numerical value I have given you about 320, 330, 340, 350 nanometer to around 700 nanometer in that range.
Oh, okay, sir.
I'm trying to open our cognitive. It is taking some time to upload. Yes. Now, children, I want to show you all these things, whatever we have discussed now here on the cognitive, what informations we can find from the cognitive. Diffraction is, yeah, you can see this diagram. Am I audible, children?
Yes,
Yes,
sir.
sir.
So see, look at this diagram. What do you see here? Wavefront is spreading out obstacles with a certain gap. When the gap thickness or width, basically, this width is equal to the incident wave, then the diffractions will be there. This sound or water wave, whatever this wave is here, it will diffract. It is spreading actually. It is spreading. Spreading means, it is not confined to one space, but is going away. It's spreading. That is the spreading. Next wave with the same distance, with the same spacing. The gap should be same when you see. No need to measure, no need to use a scale, but just with your eyes you can see that, yeah, that the distance is almost same. Even that this question, the size of a gap much larger than the wavelength, still spreading is there in the right hand side diagram, children, but this is lesser. This is lesser. This is the case that I have told you about in case of a hill. At the edges of an object, wave diffracts. So, Ajila, I want to discuss one question with all of you, and the question is, look at this question, children. Okay, let me start from B part. A wave traveling on the surface of water has a wavelength. Speed is there. Calculate frequency of the wave. Please do this question, children. Lambda is given. Speed is given. Frequency of the wave you need to calculate. The equation V equal to frequency multiplied by lambda. Frequency is given by velocity divided by wavelength. Velocity is how much? 8.0 centimeter.
8.0.
And how much is the wavelength?
2.5
2.5
centimeters.
centimeters. Centimeter cancel with centimeters. And 8 divided by 80 divided by 25. How much is this?
33.2 hertz.
3.2.
3.2, and second in hertz, or you can write 3.2 hertz. That is the answer of this question, children. And next question. The wave in B approaches a barrier that has a large gap in its center. Figure 6.2 shows the crest of the wave viewed from above. Look at this diagram. Wave, a barrier, a certain gap, and a wavelength of the wave is given. The gap in the barrier is larger than the wavelength. The gap in the barrier is larger than the wavelength. Hence, basically, they are saying this height h is greater than lambda. So we know the diffraction will be there, but a minimum diffraction is there. Minimum diffraction. Let me read what they are asking about. In figure 6.2, draw the pattern formed by the three crests after the wave passes through the gap in the barrier. You need to draw the three crests. Diffraction should be there. Diffraction will be there. A minimum diffraction. So how would you draw the pattern? Something a straight, not a curved, but Remember that the distance should be, let me try to keep it same, the wavelength actually. Something like that. So 3 patterns I have drawn here. Minimum 3 you have to show. And on figure 6.2, draw the pattern formed by the 3 curves after the wave passes through the gap on the barrier, gap in the barrier. So this is the answer for this question, children. Here the spreading is less, a minimum spreading is there, diffraction is less. In the second part, water is added to the tank and the speed of the wave in the deeper water is greater than in the shallow water. The frequency of the wave remains constant, but its wavelength is different. Read carefully this statement, children. State and explain how the wavelength of the deeper water has changed. Deeper water. We are talking about water waves. Deeper water, the gap in the barrier is larger than the wavelength. Water is added to the tank. Speed of wave in deeper water is greater. Speed is increased. Speed is increased, children. Frequency of the wave remains constant. You have to recall that equation. V proportional to wavelength because frequency is constant here. They said the speed water is added to the tank and the speed of the wave in deeper water is greater. Velocity increase. What happens with the wavelength in the deep water? As in the velocity in the deep water is increased, so wavelength will and should and must increase. So V, as V is proportional to lambda. So what you have to write in the exams, as the speed is increased in the deep water, so due to that, the wavelength of the wave will increase. Now the second part, they are talking about explain how the wavelength in the deeper water has changed. This will change. Either two possibilities are there, increase or decrease. So you have to be very careful that in what way, in what case that the wave is traveling, whether the wave is traveling in the deep water or in a shallow water. Second part, apart from the change in wavelength, describe one other difference in the pattern formed by the curves after the wave passes through the gap. Who will do this question? Apart from the change in wavelength, describe one other difference in the pattern formed by the crest after the wave passes through the gap.
That's based on the graph above, right, sir? Similar.
From this diagram, they have increased the water level. They've created a deep water. And we have seen in the part one that wavelength is increased. So instead of talking about wavelength, means wavelength increase means that the speed has increased. What other pattern? Wavelength increased, if wavelength increased, I think I can explain this question. They are talking about if wavelength is increasing. So wavelength is increasing, that is now becoming comparable to the width of the gap. So in this case,
Crest,
so it means spreading will be there, means more spreading as compared to the previous case. As compared to the previous
more
case, yeah. So more diffractions as compared to the diagram here when the wavelength was lesser than the gap. Even maybe if you find other suitable answer, you can write. It's actually that intention of showing this question, that these are the past year's question, children, and level you can see what kind of questions come in exam. We will continue with this topic, children, in our next meeting.